Hello everyone, I am Dr. Gitumoni Sharma, Associate Professor, Department of Mathematics, USTM. I am going to take a class on special theory of relativity. Today's my topic is Doppler effect. Let me talk first about keywords of my lecture. These are Lorentz transformation, consequence of Lorentz transformation, Doppler effect and aberration of Doppler effect. First, I want to say about Lorentz transformation. Lorentz transformation is the relationship between two coordinate frames that moves at a constant velocity and are relative to each other. Now, it is more convenient and easy to study that physics laws must be expressed in mathematical equation. In the 19th century, it was observed by applying a mathematical method of testing called Galilean transformation that Newton's laws of mechanics are same in S and S dash frame, but not Maxwell's laws of electromagnetism. As we have discussed earlier, Lorentz transformation gives the relation between the coordinate of a particle which moves with respect to S frame and S dash frame and whose coordinate is x, y, z, t with respect to S frame and x dash, y dash, z dash, t dash with respect to S dash frame, and Lorentz transformation gives the relation between the coordinate system. And when velocity of moving frame is very high, then the very closer to speed of light, then Lorentz transformation is applied. But Maxwell's laws of electromagnetism deeply impressed the physics all over the world. So, Einstein was also impressed by the success of Maxwell's electromagnetic theory over wide area of physics. So, Einstein convinced that a new mathematical method of testing called Lorentz transformation would have to be derived, that Maxwell's laws remain same in both frames. Now, there is a problem that when Galilean transformation failed to prove Maxwell's electromagnetic theory that they are invariant in both frames, then Einstein thought that Maxwell's electromagnetic theory is very important to us, and he was deeply impressed by Maxwell's electromagnetic theory because Maxwell's electromagnetic theory gives that light is an electromagnetic phenomenon and it has speed 3 into 10 to the power 8 meter per second. So, Einstein said that another transformation called Lorentz transformation would have to be derived so that Maxwell's laws are also invariant in both frames. There are three consequences of Lorentz transformation. When velocity of moving frame closer to speed of light, then these consequences happens. So, when velocity of moving frame faster approaches to speed of light, then there are three consequences happen in Lorentz transformation. These are relativity of simultaneity, length contraction and time dilation we discussed in our previous classes. So, simultaneous means simultaneous events are those physical events which may happen in different location, but they happen exactly in same time. If two events happens exactly at same time but different location, so those events known as simultaneous event. And relativity of simultaneity means the two simultaneous events are simultaneous only with respect to one particular observer, and they are not necessarily simultaneous with respect to the other frame of reference. That means one frame of reference say that they are the simultaneous event, but another frame of reference observe that they are may or may not be simultaneous for next frame of reference. So, that is the relativity of simultaneity. So, for example, if we have two light bulbs and light up exactly in same time, we can say that they are simultaneous event. So, that is the one of the consequence of Lorentz transformation. Next consequence is length contraction. If there are two observers who are in relative motion and they try to measure the distance between the common points, and they will end up measuring two different distances. In fact, a person who was moving with respect to reference frame will measure a distance which is shorter compared to another person who is measuring those distances in a rest frame of reference. Moving objects are shorter compared to the same object in a rest frame of reference. So, this kind of consequences is known as length contraction. In our previous classes, we discussed about length contraction. It is the L dash is equal to L divided by root over 1 minus p square by c square, where L dash is the length of the particular object with respect to S dash frame and L is the length of the particular object or particular rod with respect to S frame. So, there is a relation between the length from both observer perspective, and we get that L is equal to L dash is equal to L divided by root over 1 minus p square by c square. So, it is the length contraction. Next consequence we discussed earlier, if time is measured by two different observer who are in relative motion with respect to each other, their measurement are going to be different. Now, in classical and Newtonian physics, we think of time is absolute or very much independent of the observer in the reference frame, but in relativity little bit different. In relativity, time is very much dependent on which the reference frame is situated. So, in time dilation, what we have done, that the time measurement with respect to the moving frame is larger than the time difference with respect to the rest frame. So, we get that delta t dash is equal to delta t divided by root over 1 minus p square by c square. So, different observer get the different times in this according to this consequence of Lorentz transformation. Now, we are going to discuss about Doppler effect. The Doppler effect or Doppler shift is the apparent change in frequency of a wave in relation to an observer moving relative to the wave source. So, Doppler effect means the change in frequency of the wave between observer and the source. Doppler effect refers to the change in wave frequency during the relative motion between a wave source and its observer. So, always in Doppler effect happen between two source of the sound or any other object, then source and observer. So, it is the change in frequency. It was discovered by Christian Johann Doppler, who described it as the process of increase or decrease of starlight that depends on the relative movement of the star. The Doppler effect is a common phenomenon that we observe in our everyday lives. For instance, if you are standing on the footpath and you hear a police vehicle approaching from a distance, first the sound of the siren is faint and it gets louder as the vehicle reaches closer to you. Once the police car crosses you and goes ahead, the sound gradually decreases again. This effect is basically known as Doppler effect. So, this situation happen in case of ambulance, in case of police car, because they are siren attached in the car, and that happen. This is the Doppler effect. When source of the sound is closer to the observer, then its frequency is high. If it is passes away, then frequency is low. Generally, the Doppler effect can be defined as the change in wave frequency, whether it is light or sound, during relative motion between the source of the wave and the observer. This effect can be observed every time a source wave is moving in relation to the observer. The Doppler effect was discovered in the year 1842 by an Austrian mathematician and physicist named Christian Johann Doppler. Just I said, the effect was named after him. So, it is the brief history of Doppler effect, how it is happen. Now, an example in case of light effects, light waves. So, Doppler effect happen in waves such as light waves and sound waves. So, many waves will be there. So, in case of wave situation, Doppler effect happen. Now, we are going to discuss in case of light waves. When the source and observer are moving relative to each other, the frequency observed by the observer f a is different from the actual frequency produced by the source f naught. So, I say that in Doppler effect two main things here, observer and the source of the wave. So, observer denoted by f a and source is the source of the wave is denoted by f naught. So, when source and observer are moving relative to each other, the frequency observed by the observer FA denoted by FA is different from the actual frequency produced by the source F naught. So, initial wave frequency is F naught and observer frequency which observed by him, that it is FA. This is basically the definition of the Doppler effect in physics. Here, when the source of waves is moving towards the observer, they will have an upward shift in frequency, as for the observer from whom the source is receding, there will be a downward shift in frequency. So, there we get a change in frequency in of the wave. However, it should be noted that the effect does not occur as a result of the actual change in frequency of the wave source. The Doppler effect can be observed in both sound waves and light waves. While we have already described the effect in sound waves, the following is an example of the Doppler effect for the light waves. So, this is the picture. This picture describes how frequency and wavelength created between and source of the wave and the observer. So, this is the signal given how light passes through the medium. If we observe the light of a star from the earth, it usually shifts towards the red end of the spectrum, lower frequency or longer wavelength. So, see in this picture, it is the lower frequency and longer wavelength, and it shifted to red when it passes through medium and when it comes from star to the earth surface. When the earth and star are moving away from each other, this is also known as redshift. On the other hand, it tends to move toward the violet side, higher frequency or shorter wavelength. See, this is higher frequency and shorter wavelength near the sun or near the star. If both the earth and the star are coming close to each other, this is also called the blue shift. As a result of this phenomenon, the Doppler effect is used in studying the motion of star. It is also an integral part of modern theories of the universe. Why do we experience the Doppler effect? The main reason that we experience the Doppler effect is that as the wave source moves toward the observer, each new wave crest that is formed from the source is emitted from a location that is closer to the observer. Therefore, as the source moves closer and closer, the waves will now take less time to reach the observer, or the time between the arrivals of new wave crest is reduced. This further causes an increase in frequency. Similarly, when the source of waves is going away, the waves are emitted from a further location, thus increasing the arrival time between each new wave. This leads to a reduction in frequency. So, it is only only happens in between observer and the source of wave. When frequency high, when it is moved towards, then frequency high, and when it is passes away, its frequency is less frequency. Therefore, wavelength is longer. Now, different cases of Doppler effect. When we say source and observer are moving relative to each other, we get different cases as follow. Case 1, an observer moving away from the stationary source. Case 2, an observer moving towards the stationary source. Case 3, a source moving away from the stationary observer. Fourth one, a source moving towards the stationary observer. 5, a source and observer moving towards each other. Sixth one, a source and an observer moving away from each other. Seventh, a source and an observer moving in the same direction along the direction of the velocity of sound. And 8 is a source and an observer moving in the same direction opposite to the direction of the velocity of sound. So, there are 8 cases may be happen in case of Doppler effect. Source of the wave and the observer, and direction of the velocity of the sound or light wave. So, so many cases here, 8 cases now we are going to discuss what situation will be happen. So, this is the first case, an observer moving away from the stationary source. So, S is denoted by stationary source and O is the observer. When O go away from S, then what situation happens? So, this description is here in this picture. Now, second case is an observer moving towards the stationary source. S is stationary source and O observer, and it moving towards the source. Sound direction V. Case 3, a source moving away from the stationary observer. So, S stationary observer and O is the observer. S stationary source of the wave and O is the observer, and V the direction of the sound wave or light wave. Fourth case, when source moving towards the stationary observer. So, S source of the wave and O observer and V the velocity in the direction of the wave. And fifth case, source and an observer moving towards each other. So, S source and O observer, and they are moving towards each other. Then we need to find the velocity Vs and V naught. This is another case, a source and an observer moving away from each other. So, this shown by arrow sign. Seventh case, a source and an observer moving in the same direction along the direction of the velocity of the sound. So, S source of the wave and O observer, and they are in the opposite direction. And a last case, a source and an observer moving in the same direction opposite to the direction of the velocity of the sound. Now, we are going to discuss another example. In Sheldon's works, it is the apparent change in frequency of a wave caused by relative motion between the source of the wave and the observer. The Doppler effect is perhaps best explained visually. So, here is a thing that is emitting waves. It could be a fine track emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. So, these are all waves and they all look something like this. See, this is the picture. So, here we take a pond where a duck creating ripples in the water. These are all waves and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves in the direction it is moving, in the direction the wave fronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, this bunch of waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So, that this is the Doppler effect. See this picture. When when observer closer to the source of the wave, then it feels higher frequency, and when he moves away from the source of the wave, then he feels the lower frequency. So, this is known as Doppler effect, that is the apparent change in the frequency of a wave caused by relative motion between source of the wave and the observer. Now, another picture given here. So, now we we consider here stationary source where velocity is 0, and here wave is created, and then stationary observer where standing here which has velocity v is equal to 0. So, he observed the wave as a circle type. So, waves creating in a circle type and wavelength are same in this situation. Another example we take here, a small wavelength high frequency where a car reach closer to the observer, then here small wavelength and high frequency, and when it moves away from any observer, then it is the long wavelength and less frequency. What is aberration? Now, another important topic I am going to discuss, it is aberration. Aberration means relativistic aberration of light is a sense of the direction of a light ray when observed from various inertial reference frame. The aberration of light is an astronomical phenomenon which produces an apparent motions of celestial object. Aberration of light in optical systems such as lenses and curved mirrors, the deviation of light rays through lenses causing images of object to be blurred. We are going to prove an example for an aberration. At the outset, we prove a theorem. A plane remains a plane under a linear transformation. The equation of a plane is ax plus by plus cz plus d is equal to 0. Given equation number 1, where ABCD are constant. parameters. Now let us consider a linear transformation, that is x is equal to a1 x dash plus b1 y dash plus c1 z dash, y is equal to a2 x dash plus b2 y dash plus c2 z dash, and z is equal to a3 x dash plus b3 y dash plus c3 z dash. It is equation number 2. So first what we have done, so first we consider a plane equation, and we are now going to show that it is unchanged, it is invariant, and after transformation it will remain same. So we get another equation which is a plane, where a small a1, b1, c1 etc. are constant. Using equation 2 in equation 1, we obtain an equation of the form a dash x dash, capital A dash x dash plus b dash y dash plus c dash z dash plus d dash is equal to 0. It is equation number 3. So equation 3 also represent a plane in the new coordinate system. So first we consider one plane equation which is given by equation number 1, where a, b, c, d are constant, and in the under transformation when we have taken x is equal to a1 x dash plus b1 y dash plus c1 z dash, similarly y is equal to a1 x a2 x dash plus b2 y dash plus c2 z dash, and z is equal to a3 x dash plus b3 y dash plus c3 z dash, then we after substituting equation 2 in 1, we get another equation which is a dash x dash plus b dash y dash plus c dash z dash plus d dash equal 0. So given equation number 3. So 3 is another equation of a plane, and only difference is that in first equation our constant parameters is constant parameters are a, b, c, d. Here a dash, b dash, c dash and d dash. In the S dash frame is plane. Equation 1 is a plane wavefront of a monochromatic plane light wave of wavelength lambda dash and frequency nu dash of unit amplitude emitted from a source at O and O dash at the moment of coincidence of O dash. So O dash and dash. Now we consider a wavelength in two frame where we show that the how it is how aberration happens in case of Doppler effect. O dash n dash is a ray or a wave normal which makes an angle theta dash with x dash axis. The wavefront is such that it is parallel to the z dash axis. Therefore, the rays are in or parallel to the x dash y dash plane. So, if we consider two frame x y z axis and x dash y dash z dash axis, and if we consider a wavefront which is denoted by AB, then in the S dash frame it is denoted by A dash B dash, and here O dash n dash is a ray. O dash n dash means origin to the perpendicular distance between origin and the wavefront A dash B dash. Then it is a ray and it makes an angle theta dash with the x dash axis. The wavefront is such that it is parallel to the z dash axis. Z dash means x dash y dash plane. So we need to imagine the plane x dash y dash z dash plane. The expression of the wave of a unit amplitude is sin twice pi into x dash cos theta dash minus y dash sin theta dash divided by lambda dash minus phi dash t dash, given equation number 4, and we know that lambda dash nu dash is equal to c, light velocity always wavelength into frequency. According to the theorem proved above, a wavefront AB in the S frame corresponding to the plane wavefront A dash B dash in the S dash frame is also a plane. So, the expression of the wave in S frame can be written in the form in S dash frame. So, already we proved that a plane remains unchanged under the linear transformation. So, using this theorem we can write the same expression of the wave in the S dash frame. Equation 4 is the expression in S frame with respect to the rest frame, and same expression we can write with respect to S dash frame. This is given by equation 5, sin twice by x cos theta minus y sin theta divided by lambda minus Vt. In equation 5, we know that lambda nu is equal to c, and lambda is the wavelength, nu is the frequency, and t is the time with respect to S frame. Now, we apply Lorentz transformation equation. Again I remind you, Lorentz transformation equations are x dash is equal to x minus Vt divided by root over 1 minus v square c square, y dash is equal to y, z dash is equal to z, and t dash is equal to t minus vx by c square whole divided by root over 1 minus v square by c square. So, we putting the Lorentz transformation equation in equation 5, we get sin twice pi. In place of x dash, in equation 4 we put the Lorentz transformation equation. So, instead of x dash we put here x minus Vt whole divided by root over 1 minus v square by c square, and instead of t dash we put here t minus vx by c square whole divided by root over 1 minus v square by c square. So, after simplification we get the expression sin twice pi into 1 by lambda dash into x minus Vt divided by root over 1 minus v square by c square cos theta dash plus y cos theta dash by lambda dash minus nu dash into t minus vx by c square whole divided by root over 1 minus v square by c square. On rearranging the term, we get equation 6, which is sin twice pi into cos theta dash plus v by c divided by lambda dash into root over 1 minus v square by c square whole term into x plus sin theta dash by lambda dash into y minus v by c cos theta dash plus 1 whole into v dash whole into nu dash whole divided by root over 1 minus v square by c square into t. So, it is given it is equation number 6. Now, try to understand that we get the same type of linear transformation x, y, t, and in equation 4 we get here in equation 4 it is also x dash y dash t dash. So, replacing x dash y dash t dash value we get the we get one term in terms of x y t. Obviously, equation 5 and equation 6 would be identical, hence equating the coefficient of x y t we get cos theta by lambda dash is equal to cos theta dash plus v by c whole divided by lambda dash into root over 1 minus v square by c square given by equation number 7. Equation 8 is sin theta by lambda equal sin theta dash by lambda dash, and equation 9 gives that nu is equal to nu dash into 1 plus v by c cos theta dash whole divided by root over 1 minus v square by c square. Now, see the difference between the equation. So, in first equation we get a relation between cosine of the angle theta and theta dash. Theta is the angle made by the ray with x axis, and theta dash is the angle made by the ray with the x dash axis. Similarly, in equation 8 we get a relation between the angle theta and theta dash, and same thing, the theta angle made by the ray with the x axis and theta dash with the x dash axis, and equation 9 is the relation between nu and nu dash. So, nu is the frequency which is observed by the race frame, and nu dash is the frequency which is observed by the moving frame. Now, dividing equation 8 by 7 we get tan theta is equal to sin theta dash into root over 1 minus v square by c square whole divided by cos theta dash plus v by c. It is equation 10. This shows that how the direction of the ray in the S frame deviates from the from that of the ray in the S dash frame. This is called the phenomenon of aberration of light. So, this is the main equation, relativistic equation, which gives the which gives how light deviates from a source of wave, and this is known as relativistic equation of the aberration of light. Equation 10 is called the relativistic equation for the aberration of light. I just say. Now, the equation 9, nu is equal to nu dash into 1 plus v by c cos theta dash whole divided by root over 1 minus v square by c square is called relativistic equation for the Doppler effect. Dear Doppler effect, because here we see that a relation between the frequency with respect to S frame and with respect to moving frame. So, nu dash is the frequency with respect to moving frame and nu is the frequency with respect to S frame. So, it is the relativistic equation for Doppler effect. Now, there are two particular cases in Doppler effect that are longitudinal Doppler effect and transverse Doppler effect. Again, from this equation, if we interchange nu and nu dash, then we get another equation. It is nu dash is equal to nu into 1 minus v by c cos theta whole divided by root over 1 minus v square by c square. It is equation A, and from this equation we get the particular cases longitudinal Doppler effect and transverse Doppler effect. Longitudinal Doppler effect for theta is equal to 0. See, in this equation, when theta is equal to 0, then cos 0 will be 1. Then we get nu dash is equal to nu 1 minus nu by c into 0, 0 whole divided by cos 0 equal 1, cos 0 1 whole divided by root over 1 minus v square c square. So, we get the relation, we get after simplification nu dash is equal to nu is equal to nu dash into root over c plus v whole divided by c minus v. So, c is the speed of light and v is the moving v is the velocity of the moving frame. In this case, the source and the observer move towards each other. So, it is the longitudinal Doppler effect. Then in that case, in this case, the source and the source of the wave and the observer moving towards each other. So, in this situation, mathematical form we get nu is equal to nu dash root of into root over c plus v divided by c minus v. For theta is equal to 180 degree, we get nu is equal to nu dash into c minus v root over c minus v by c plus v. In this case, the source and the observer move away from each other. So, their distance will be large, and then that situation happened that nu is equal to nu dash into root over c minus v divided by c plus v. And for the transverse Doppler effect is that theta is equal to 90 degree. From equation A, we get after simplification nu is equal to nu dash into root over 1 minus v square by c square. This effect occurs when v is sufficiently large, so that the term v square by c square is negligible, and then it can be then it will be nu is equal to nu dash. So, this situation happen and it is known as transverse Doppler effect. Thank you.